Hello, good evening. Am I audible? Hmm. My name is Devmallo Roy, and I will be conducting today's live session. Uh, so, uh, the session is for the course of Introduction to Fluid Mechanics, which is instructed by Professor Suman Chakraborty. And in this week's live session, we will be discussing problems from assignment 3, uh, uh, which is based on the topics of surface tension and hydrostatics. So, we'll start. We'll start with the first question. So, am I audible? Can you please confirm if my voice is audible or not? Hello. All right. So I'll continue. Okay. Uh, so let's continue with the first question. So here we will be mainly dealing with the concept of surface tension. So the first question is basically uh, the absolute basic definition of based on the absolute basic definition of surface tension. So we have a soap film here which is strapped between a frame and a wire of length 10 centimeter. So which length is 10 centimeter? This one. So this length, this L if I say. So this L, this is equal to 10 centimeter. And what is basically happening is this mass M is there and gravity is acting. So this mass is balanced by this soap film, and uh, this weight provided by this mass is balanced by the surface tension provided by the soap film. So to solve this problem, we must understand what surface tension is and how does it act. So, like if we consider this soap film, so this area is covered by the soap film, and it has two surfaces. One is this, the one towards the screen, and one is away from the screen. So, like if I draw a different view, so suppose this is the wire. So this is the wire, and this is the soap film. So this is the soap film. And this weight is hanging like this, so you can understand which like it is as if I'm looking from here. So then you will see something like this: the mass is hanging here, the gravity is acting this way, and this is basically the wire and the software. So here this force, it is mg that is acting. Now here, uh, this uh, there will be surface tension which will counteract the weight of this. So surface tension will act tangentially to the surface of the film. So this is the liquid. Uh, we will, let's say, surface tension, like let's represent it with uh, sigma s. So both sides this sigma s will be acting. So this is force per unit length. So this will act uh, along this wire throughout this length. So let's say, let's represent it in gamma. That is more standard of a notation. So, so let's represent it using gamma, and this is acting uh, along this whole length. So the force on the upper surface of the software will be gamma into L, and bottom surface will also be gamma into L. So this 2 gamma L, this will be equal to mg. So this is the force balance equation for the wire. If at equilibrium the wire is stationary, this is basically the balance of the forces acting on this wire. Now our gamma is given, the surface tension is given as 0.072, and length of the wire is also given. L is given as 10 centimeter. So what we have to do is find the value of M. We know G. So we can simply put in the values. It will be 2 into 0.072 into 10 centimeters, which is zero point 0.1 meters. So I have converted everything into SI units. So M and G is 10 meter per second square. So if I if I calculate this, then what will it be? Point. This is 1.44, right? This is 1.44. So this was 10 to uh, 10 to the minus 1. If I multiply 2 into this, so there it's 10 to the minus 3. So the answer should be option C. The closest answer is option C here. So this will be the correct answer. So this is how we solve the problem. Hmm. If you have any doubt, please convey. Okay, you are. This is an interaction session, so you are like free to unmute yourself and ask your doubts, and we can have a discussion on not only this problem but related to this topic or any of the previous topics that we have already discussed in previous live sessions. So any of those problems, if, any of those topics, if you have any questions, any queries, this is the place for the discussion. All right. So yeah. So here the explanation of this is given, and like they have come to the same answer. So let's now before moving on to the next question, which first few of the questions are related to the same topic, that of surface tension. Let's first try to understand what actually was happening when we solve this problem. So how is surface tension defined? So it can be defined in two ways. One is by the force per unit length definition of the surface tension that we just used right now. So to extend the surface, uh, you have a particular surface area, right? So if to extend the surface along this length, along the edge of this surface, the force that you have to provide per unit length of this uh, of the edge, that is one definition of surface tension. So we have a liquid surface here, in let's say the top of the soap film. We have a liquid surface here. We want to extend this liquid surface. We want to increase the amount of surface area, the interfacial surface area. So this is the interface between air and uh, soap water. So if we want to increase this, we need to apply a certain amount of extra force. So that force per unit length, edge length, is my surface tension. It also can be expressed in another way, which is via energy, and that is a more fundamental and more popular definition. So it is defined as in the increase in energy uh, per unit uh, increase in area. So, if we increase the amount of interfacial area, there will be an energy associated with it, and like increasing that area will the per unit area, whatever the energy needs to be supplied to increase the interfacial area, that is called the surface tension, and it originates from, you must have uh, come across this figure, like suppose, let's say we have a fluid particle inside the bulk of the fluid. So if it is inside the bulk of the fluid, there are other fluid particles nearby. So this fluid particle undergoes some attraction forces from the other particles, other fluid particles, and that is uniform in all sides because it is completely surrounded by other fluid particles. Now, what happens if this particle is near the interface, that is near the edge of this fluid? So if it is near the edge, it will only find fluid particles at one side, and the other side will be a different fluid. Like for example, here it will be air, so it might not have the same attraction forces uh, towards the air. So there will be a net downward force, which is basically trying, like if you see, it is acting on each and every particle on this interface, and this net downward force will is what is trying to minimize the surface area of the this interfacial surface area, and that is the origin of our surface tension. So whenever uh, we are increasing the interfacial area, we are increasing the number of molecules in the interface which are like trying to escape from the interface and come to the towards the bulk of the liquid. So this also, this surface tension also results in something called Laplace pressure, or like a jump in pressure across the interface due to this excess force. We will come to that in this assignment itself. So if there is any question, like, feel free to ask. So this is the next question. In the arrangement, you can see is very similar to the previous one. So here also we have this L. This is given as 8 centimeter. So we have this length of this movable slide, 8 centimeter. Here we have to find out the surface tension. The force is given. The force that is required on this movable wire to keep this at equilibrium, that is given, and mm, and we have to find the surface tension. So we will again use our same equation. So 2 gamma L, 2, because there are two surfaces of of this film. There is a one top surface and another is the means there are two surfaces of a film. In between those two surfaces, the liquid is present. Mm. So here, instead of mg, there will be like the force applied, which is given. So we have to find gamma. So we will take gamma on one side, and the others will be in the other side. So this is 3, 2 into uh, minus 2, because it's centimeter, 8 centimeter. Hmm. So what we have here is 1.5 if we take the numericals, and the exponent, it is 10 to the power 10 to the 5. So let's see. Uh, so I don't think this is supposed to be kilonewton. Yeah, means from the solution here we can see like this is actually 0.024. So I can make a correction. This will be millinewton in 10 to the power minus 3. And that makes much more sense because kilonewton is a lot of force, and like like physically that much force will not be required to uh, equilibrate a film with one surface edge of 8 centimeter. That's a lot of force. So if I update this, then this is 10 to the power 10 to the power minus 1, right? 10 to the power minus 1. So this is 0.15 Newton per meter. And this is much more a reasonable value. Okay. Here the this uh, figure is also given, so this figure is more representative of what I drawn earlier. So the liquid is inside, and there are two surfaces basically attached to the wire, and the forces due to the surface tension are acting tangentially. Uh, if there had been some bulk of fluid, so that this like film would have been different, or maybe like this is not a film, this is a whole like container, then things can be definitely different. But like this setup is very popular in measuring surface tension. So here, like a film is used, and like the force is applied to equilibrate it, and we can calculate the surface tension from here. So we will go to the next question. So this is another classic problem, which is capillary rise. So here what we are doing is we are placing a capillary tube inside a bulk of a liquid, and we are seeing the liquid rises along this capillary. Now what is happening basically is that this the capillary surface, the capillary surface, the contact angle, uh, like there is a three-phase contact angle between air, hmm, air and this liquid and this glass. So capillary, say, it's made of glass. So these three phases, they meet at a point. Now at this point, what is happening is uh, we have an interface like this. Hmm. We have an interface like this. This is glass. This side is glass. Let's say this side is the liquid, and this side is air. Now, as we have already seen, there is a surface tension associated with the air and the liquid. So there will be some stresses, uh, stresses contributing here uh, for. I think someone is trying to join. Yeah, I will continue. Hmm. So at this interface, so we have three interfaces here. So the surface tension accounts for the interfacial stresses between the air and the liquid. Similarly, there will also be surface stresses between liquid and glass and air and glass. So we will also have some stresses associated with these interfaces. So this, let's call as L. Uh, so this is solid. So S, let's say, and like this is GS, gas and solid, and this is well, so there is a stress balance which is occurring here. Now, what uh, this stress balance due to during equilibrium, this will balance each other out. So, like there are we can for our standard force balance, we will do the same thing. We will equilibrate it in the vertical and the horizontal direction. Hmm. So let's equilibrate. If we equilibrate in this horizontal direction, what happens is basically we see that like if this angle is theta, then this gamma ls plus uh, uh, so this is ga, yeah, gamma ls plus gamma gl cos theta, this is equal to gamma g. So if we know the interfacial stresses, then we can find out what is cos gamma gl. So gamma gl, we can definitely, this is the surface tension between the air and liquid. We have other methods to find this out. Like the previous problems that we discussed. If we have a liquid film and we are applying a force on a wire, then uh, uh, from force balance we can calculate gamma GL, and this and gamma SG and LS. So these are basically the surface tension, the interfacial stresses between the glass and liquid and glass and air. So these individually are not that important, but like this difference between these stresses are uh, essential, so that we can like if we find out cos theta, we can easily find out what is the value of this, the difference between these stresses. And how can we find cos theta? Here this our experiment with this capillary rise comes into the picture. Okay, now you may also ask what happens in the vertical stresses. So we have balanced the horizontal stresses and we have got this equation. But we should also ideally also keep in mind the vertical stresses. So obviously there will be a sin theta component, but this is applied on glass and glass is a solid, so its deformation will not be much. So so basically what happens is the surface tension is definitely applying some force on this glass which is trying to pull it upwards, but glass being a very rigid substance, being a solid, it's not deforming due to this stresses. However, if you had a much softer solid here whose modulus of elasticity is very less, then yes, you may actually also see some contact angles like this, where like this is the liquid and this is the gas and this is the solid, and the solid has been pinched up due to this vertical force balance. But this is not really in the scope of this particular discussion here. Here only, like you can know that because this solid is very rigid, it's not deforming, and thus we are not considering the vertical force balance. Vertical force balance is not of importance to us. Okay. Now, what we will do to find cos theta, uh, we will solve this problem of capillary rise. So here, this contact angle theta is there. Hmm. And this the surface tension force is basically holding the weight of this liquid up. Hmm. So let's find out the weight of this liquid. So if the height is h and the radius of this capillary tube is r, so the volume is h pi r square, right? This is the volume of a cylinder, and for mass we will multiply it with density, rho. Rho is the density of this liquid, and g will be multiplied for the weight. So this is the weight of the uh, resin liquid. Now we will equate it with the surface tension, total surface tension force acting. So the total surface tension force will be acting on the edge of this capillary. So we will take the length, which is 2 pi r. Hmm. We'll take the surface tension, which is gamma. But since this contact angle is there, only one component of the surface tension is acting, which is the cos theta component. So we'll take cos theta. So these two are balancing each other out. Hmm. So from here, we have to find out cos theta. So let's move to the next slide. Here, this expression is already given, but I will again write it down. Pi r square rho g. This is equal to 2 pi r gamma cos theta. So either you can remember this, or you can simply do the force balance every time. I think like doing the force balance every time will clear up your concept of how we are actually like getting it. So you don't have to really remember expressions of capillary height using this standard formulas and all. You can simply in one line uh, do this force balance, and from here you will get the cos theta. I think like here you have to find the h, but here from here like H is, you can see it's measurable. Generally, when you are doing such experiments, H will be measurable. You can calculate cos theta from here, or you can calculate gamma from here if you don't know gamma, but you can like geometrically find out cos theta, and you can find out gamma from here as well. But here in our question, we are asked to find out H, so we will find out H. The pi's will cancel, so this will be 2 gamma cos theta divided by rho g. We will put the values, and here they have already put the values. Get this. If you have any question, please ask me related to this or any related topic or questions. I'll move to the next question then.
Sir,
Yeah.
in that case, we have taken the water as a, the water is rising. So, what if
Mhm.
we take the mercury? In that case, the meniscus will be upside down. So,
Yes.
will that formula be applicable?
Yes, definitely. So, what will happen in the case of mercury? Uh, as you said, mercury, it will dip, right?
Yes,
It
sir.
will dip. So, you have the capillary here, and this has dipped. Hmm. So here, what is happening? The pressure at this point. Hmm. So this is basically, there is a dip in the mercury. So there a pressure at this point is higher compared to the pressure at this point. So like you have the atmospheric pressure, right? The atmosphere. Hmm. You have atmospheric pressure at this surface. Correct. Now, what is the pressure h distance lower? H distance lower, the pressure will be rho of mercury. Rho mercury G H. Right.
Yes, sir.
This is the pressure. So pressure into this area. So let's say pi r square. So this is the amount of force that this is exerting. Correct.
Yes, sir.
This is the amount of force that this is exerting on this particular surface. Now this you will equate with your surface tension force. Here the surface tension force will be 2 pi r gamma cos theta, right? But here the theta is obtuse, right? Theta is obtuse, that is, it is greater than 90 degree.
Yes, sir.
So the cos theta value will be negative, correct?
Yes, sir.
The cos theta value will be negative. So here, for to account for that, you will have to like use a minus sign, because the force is acting on the other direction. Hmm. So like if you are taking force on this particular fluid, the force on this particular fluid will be this side. Hmm. So upwards, so downwards, sorry, downwards. To the glass it will be upwards, to mercury on glass will be upwards, and mercury the glass will be applying a downwards force, right? It is applying a downwards force which is balancing the pressures upward force. So you
Yes, sir.
see, you get a formula here. You have just the minus sign, since this cos theta is negative. To counter that, you have a minus sign. But you see, like this expression, the expression that you got here, this is actually exactly same as this expression. Correct,
Yes, sir. Yes, sir.
right? You still have this h pi r square rho g. Why is that? Because here also, what we are basically doing is we have atmospheric pressure here at this point. Now, since this water is rising, we have lower than atmospheric pressure at this point. So this is kind of trying to suck it in, right?
Yes, sir.
Here we still have atmospheric pressure, and here we have a lower than atmospheric pressure. How much lower? We have rho, this liquid, into G into H. this much lower pressure compared to atmospheric. So this is trying to suck this air, this meniscus inside, and that is balanced by the surface tension force, which is trying to pull it upwards. So the concept here is same, just the direction of the forces are changing. Here the pressure is acting downwards, there the pressure is acting upwards on the meniscus.
Yes, sir.
Any other question?
No, sir.
Okay. So yeah, let's go to the next question. So consider a zero point 0.5 diameter air bubble in a liquid. Determine the pressure difference between the inside and outside of air bubble if the surface tension at the air liquid interface is 0.08 Newton per meter. So here we have an air bubble. So what is a bubble? So bubble consists of actually two spheres. So two concentric spheres, we will assume it to be concentric. So two concentric spheres. The liquid is contained between these two spheres. So here is the liquid, and we have air outside and inside. So here they have asked to find the pressure difference between inside and outside the air bubble. So like if this is P2 and this is P1, they have asked to find out P2 minus P1. So here also the same thing will happen. So because of the surface tension, there will be an excess pressure. So what generally happens is, like if you have a curved surface, like we had in this case itself. So if we have a curved surface, then like let's like take, means here the whole surface is curved. So we are like you can assume we are cutting a segment. We are cutting a segment of this sphere. Let's say we are cutting out this segment, and we are analyzing this particular segment. So this is a curved surface, and at the end of this surface, there is surface tension forces which will be acting. So, like if it is a spherical cut, it is a three-dimensional cut. So, like each and every direction, there will be some forces which will be acting. Hmm. So, net force of on this curved surface will be downwards, right? And this downwards force needs to be balanced by a pressure difference inside this curved surface and outside this curved surface, because this is in equilibrium, this is not moving, so the forces must be balanced. So if the pressure outside is P1 and inside is P2, there is a relation which is given as P2 minus P1. This is equal to gamma 1 by R1 plus 1 by gamma is the surface tension. What are R1 and R2? R1 and R2 are geometrical considerations. So let's say like we have a film like this. Hmm. So if I take any two orthogonal curves, then there will be a circle that these curves are part of, right? So the radius of those surfaces are R1 and R2. So like I can if I think give an example, then this concept will be more clear to you. So let's say you have a sphere. Hmm. Let's say you have a sphere. Then you take any point. You draw like a circle around this. So what is the radius of this circle? The radius of this circle is r, which is the radius of this sphere, right? Any point you take, and you just draw a circle around this. So this will be r. And if you take a 90-degree angle and you draw a circle around that, then also the radius will be r. So here the r1 is also r and r2 is also r. Hmm. But if you take a cylinder, for example, you take a cylinder here, if you take a point on this cylinder and draw a circle around this, so what is so this will be R1. Let's suppose the radius of the cylinder is capital R, so this is R. But what about R2? R2, for this we have to draw a perpendicular line. But this perpendicular line is not a circle, this is a straight line. So what is the radius of a straight line? That is infinity, right? So like this is part of, we will consider that it's a part of a very very large circle. So the radius here is infinity. So here R2 will be infinity. So here the surface tension, like if I put this equation, so this is the equation. So if I put it in this equation, the pressure difference will be sigma by R in case of the cylinder. In case of the sphere, what it will be? This is 1 by R and this is also 1 by R. So this will be 2 sigma by R. Okay, is it clear?
Yes, sir.
Okay. So here, so if this is clear, then we can easily solve this problem. So here we are encountering two interfaces. So this is like one. Uh, so what will be the pressure inside this liquid portion? Inside this liquid portion will be whatever this P1 is, P1 plus 2 sigma by R, right? The excess pressure upon like encountering this first interface will be 2 sigma by R. And once we jump the next interface, we come inside, then there will be an additional 2 sigma by R pressure jump, right? Because
Yes,
we are
yes.
again coming inside an interface. So this will be our P2. So our P2 minus P1 will be 4 sigma by R. We put the values. We have, this is our gamma. Sorry, uh, gamma is this given, and R is this is the diameter. So this is 2R. This is given. So if we just put in the values, they have already done this. So if you put in the values, you should get. Okay. So that's how like excess pressure is being formed inside the bubble. So what would have been the excess pressure if it was just a droplet? So droplet, the whole surface is liquid. The whole inside is liquid, and it is floating in air. For example, like a raindrop. So the whole inside is liquid. So what will be the pressure inside this excess pressure? P2 minus P1. So outside it is P1 and inside is P2. Here we are only encountering one interface. So what will be this? This will be 2 sigma
2 sigma by R.
by r, 2 gamma by r. Yeah, whatever like sigma you can make. If it were an like ellipsoid, if it were an ellipsoidal droplet, Hmm. So these kind of droplets you can have if there is some background flow going on. Like for example, this is inside an extensional flow, so air is flowing like this. Hmm. So in many turbulent flow situations, you may have such droplets where it is not particularly spherical in shape. This is ellipsoid in shape. So there is uh, here we have to specify the radius of curvature for this the two sides. Hmm. So if one is R1 and another is R2, then our pressure here, the pressure drop will simply be gamma 1 by R1 plus 1 by R. So whatever be the geometry, this pressure drop can be found out. Hmm. Here also, like you will see that the pressure drop for like each and every point might be different. So there are maybe some other flow physics uh, that are uh, going on here. Some maybe is some internal flows which is trying to balance out this pressure difference. Hmm. Like in more advanced courses of fluid mechanics, you may come across such situations. So let's go to the next question. So yeah, you have a question for Mercury as you were asking earlier. So here, this is an assertion reason type of question. So the first statement is the mercury level inside tube shall rise above the level of mercury outside. And the next reason is cohesive force between the molecules of mercury is greater than the adhesive force between the mercury and glass. So yeah, can you tell me if like first statement is correct or wrong? First is wrong, right? Because
Yes, sir. First, yes, yes. I agree with
hmm,
down.
yeah, mercury will dip. So it will be a capillary rise situation. It will be uh, dipping it. And what about the second statement? It is saying the cohesive force between the molecules of mercury is greater than that of than the adhesive forces between mercury and glass.
Yes, sir. It is true.
It is true. Why?
Because of the mercury is moving, right? So
Hmm. Yeah, so basically, like this is the this is your definition of surface like surface tension. Hmm. So mercury, first of all, uh, like since its contact angle is obtuse, it does not like glass, right? That's why
yes,
its contact angle is obtuse. It is trying to minimize the surface area between glass and mercury. So if you put a mercury drop on glass, it's a very bad drop. Yeah. So if you try to put a mercury on glass surface, then it will behave something like this. So the contact angle here is obtuse. Hmm. And why is this like this? Because it does not like glass. Hmm. The energy, the surface energy, the interfacial energy between glass and mercury is very high. So it tries to minimize that energy and it is avoiding contact with glass as much as possible. So that is only indicative that your cohesion force between mercury between molecules of mercury is definitely greater than adhesive forces between mercury and glass. Hmm. But it is this statement is actually true also for water because the interfacial energy there is a jump in like the interfacial energy if it is like positive there is some energy on the interface then only this statement is true. Hmm. So, cohesive forces between same molecules, like water and water as well, is greater than adhesive forces between, like for example, water and glass as well. So, cohesive forces in general are stronger. However, there are exceptions on this, and like there are surfaces which completely wet, and there are molecules which actually have higher adhesive forces between other molecules than with itself. But in general, like most for most materials, you will see the cohesive forces between the same type of molecules is greater than adhesive forces between two different types of molecules. Now, what will be the answer? Like if the question here is changed to like adhesive forces between mercury and glass, and let's say adhesive forces between mercury and air. Uh, sorry, mercury, not mercury, glass and air. Glass and air. So if we compare this, then which one will be greater? Glass and air forces are is greater, or mercury and glass forces are greater?
Glass and air process.
Glass's air is greater because glass likes air likes glass more than the mercury. That's why the contact angle is like this. Now, if it were water, so glass and air and glass and water, then glass and water will be higher because for water your contact angle is acute. Hmm. So your contact angle is acute. So water tries to tends to like glass more compared to air and glass. So the interfacial energy between water and glass is lower compared to air and glass. So this is the concept. So this is true, right? This second statement is true, and first statement is false. So, yeah, this one. A is false, B is true. Hmm. So here they have represented the dip in mercury capillary, uh, the capillary dip for mercury. Yeah. So next question. So next question is pressure on given mass of liquid is increased. The density of the liquid increases while temperature remains constant. So, what is the average value of bulk modulus of compressibility of the liquid over this given pressure? Okay. So, like to solve this question, what you need to know is basically the definition of bulk modulus. So, so do you know the definition of bulk modulus? So, like this can be like simply defined as how much pressure is needed to change the specific relative density. So, like, if you have some d rho by rho, this is the change in density by density, and how much pressure is needed, dp. So, change in pressure needed for this relative change in density. So, this is simply your bulk modulus, and of this actually occurs at constant temperature. So, like if you really write it properly in thermodynamical terms, this is a partial differential. Partial because there are other state variables like temperature. So here temperature we are keeping constant. It is simply dp by d rho. Hmm. So here they have given the change in pressure, they have given the change in density. Like we will simply assume that this del rho is delta p, and so del p is delta p, and del rho is delta rho. So we'll simply like let's assume this density to be 500. Hmm. So the change in density is not that high, so we'll assume it to be 500, and change in density is like 1, and changes in pressure is zero point 0.5 megapascal. So zero point 0.5 into 10 to the 6. So this is basically the this is basically the bulk modulus. So this will be 2.5 into 10 to the 8 pascal. So this matches with the option B. So all you need to know here is the definition of bulk modulus. Bulk modulus basically defines the compressibility of the compressibility of the fluid. Hmm. So the pressure, if a pressure is applied and its density is changing due to this applied pressure, that means the fluid is compressible, and the degree of compressibility is defined by the bulk modulus. Okay. Hmm. So here, from here, like we can also uh, have the like definition of the Mach number, and how Mach number is influences the compressibility. Like for a flow, if uh, so, have you done that exercise in your class? classes where like using Mach number, you try to predict whether a flow is compressible or not.
Yes, sir. They have discussed.
Yeah. So can you tell me how that comes across? So basically here, like we have this bulk modulus and we have rho. Hmm. Uh, and this bulk modulus is related to the speed of sound. How? The speed of sound can also be defined like this, right? Hmm. From like if we consider the if we consider an adiabatic the like propagation of disturbance or propagation of sound as an adiabatic process, then this is the uh, this this is the velocity of sound. Now, if I simply replace this, then your a square is uh, uh, is becoming this, right? Del p del rho. Hmm. And this del p like for a for a if the pressure the change in pressure is due to the flow of a fluid, then this will be like given by half rho v square. Hmm. If this is like given by a flow. Hmm. So from Bernoulli's equation, we can like say like um, we can have an estimate that this pressure change, if it is due to a flowing like due to flow, not an applied pressure, an externally applied pressure, then this will be in the order of half rho v square. Hmm. Half rho v square, and this is uh, del rho. So basically, what we have this del rho by rho. This is this like relative change in density. So this is basically what defines our compressibility. So this will be half v by a whole square, and this v by a is our Mach number. So from here we can like relate our compressibility of a of a flow compressibility to the Mach number. So this analysis that we just did, this is for like uh, not for applied an applied pressure situation, like it is not for piston cylinder thing. So in a piston cylinder, what we are doing, we are applying an external pressure through the piston, and we are compressing the fluid. But here, what we are discussing is basically the compressibility of a flowing of a flow. So the pressure change here that we are discussing is due to the due to a flow. So if a flow is compressible or not, we can judge by the Mach number of the flow. Okay. Yeah. So here they have given the solution to this question. Okay. Let's move to the next question. So this is based on your hydrostatics. So you have to find the pressure of the this chamber, pressure inside this chamber. Hmm. So the like way to basically do these problems are just define these points. Hmm. So let this be like P1, hmm, this be P2, and this be P3. Hmm. We have to find P3. So let's start with P3. Hmm. Uh, so let's start with P1 actually. P1 we know, right? So let's start with P1. Hmm. Uh, so this is P1. What is P2 then? P2 is basically a higher pressure. How much higher? By this rho GH. Hmm. So rho is given, I guess. Yeah, specific gravity is given. Specific gravity is basically like the density related relative to the density of water. So from the specific gravity, we can find out the density. So density of water is 1000, so density of this fluid is 850 kg per meter cube. So we can use that. So rho gh is this P2. Oh, yeah, there is no need of P3. Sorry. Yeah, this is the same fluid. So here the pressure is. We will assume the pressure is same. We will, like, since gas is given, so they have uh, used the term gas. So we will assume the pressure to be uniform here. Why? Because the density of gases are extremely low compared to the density of fluid. So we will like neglect the whatever rho gh variation uh, this gas will uh, the mass of the gas, whatever the uh, uh, pressure variation due to the mass of the gas, we will neglect because the density is much less compared to the density of the fluid. So have we simply have to calculate this. So this is P1 is given as 96 kPa. So 6 to 10 power 3 and rho gh. So 850 to 10 into h is 0.55. Yeah. So you can calculate this. It's it's calculated here. Yeah. So you can put these values and find out whether this is correct. So is this matching? Have you done these questions previously?
No, sir, this is not assignment questions.
Okay, okay. Mm. You can put this value. So 85 into 55 you have to calculate. If you have a calculator in hand, you can check whether the values are correct or not. Yeah. So I am getting 4.6. So this as 4.6. So 96 into 10 to the power 3 plus 4.6 into 10 to the power 3. So this is 106, 100.6 kPa. This is correct. So this is a similar question. Can you attempt this question if you have not done this question already? So can you attempt this question?
Sir, here we have to consider 3 points, right?
Yeah. So here there are total three liquids, right? Three. So this is mercury, oil, and water and air. So this air pressure we have to find out, I guess. Which pressure we have to find out? Determine air pressure of in the tank. Yeah, we have to find out this pressure. So, so this point pressure we have to find out. So this is marked as one already. So we need to take this point, and this point is already given. So total 4 points are there. This is marked as P2. This is marked as 1. So let's say this is 3 and this is 4. So can you tell me what is P3? Like the expression, I do not know, need the values. So the expression what it will be in terms of P2. So P3 is P2 then plus
Plus P4 plus P1.
hmm? Tell me.
So P3 is equals to P2 plus P4 and then P plus P1.
Uh, P3 is equal to. So what we have to do is we have to like play with the known quantities. So let to find out P3, we know P2, right? And we can get P3 using the concept that it is holding up this part of the liquid, right? This H3. You can see, right? Is
Yes,
it
sir.
it's visible, huh? So H3, it is holding up. Hmm. So this weight it is holding up. So what is the pressure due to this? The pressure is rho of mercury here. This is mercury. So rho of mercury into G into H3. Hmm. So P2 plus this will be rho Hg G H3. Is this concept clear? How I found out P3?
Yes, sir.
Hmm. So can you tell me what is P4? We know P3 now. We know P3. So can you tell me what is P4 in terms of P3 and these geometrical parameters like the height and density and all? Hmm.
It will be P3 minus rho of water into G into H2.
Hmm. So why minus?
Because sir, P3 is P3 is P3 has at more pressure, no sir.
Yes, P3 has more pressure. Hmm. So because it is lower, like it's
Yes, sir.
it's at a lower point. So P3 minus. So this is rho of oil. Hmm. So this fluid in between is oil.
Oh, yes, sir.
So oil G into H H2, right?
H2. Yes, sir.
Hmm. So what is P1? P1 then that the thing that we have to find.
P4 minus P, P rho G H1.
P4 minus rho G H1. Hmm, that's correct. This is like P1 is also at a higher point, so this will be minus. Hmm. So rho of water here.
Rho
Hmm.
of water. Yes.
Rho of water G H1. Hmm. So you can put the values and find out. Hmm, that is not a problem. So all the densities are given. So the densities are given and this H are given. H, H1, H2, H2. And atmospheric pressure is given. Atmospheric pressure is which one? P2. P2 is atmospheric pressure, right?
Yes, sir.
Hmm. So from there you can find out this. All right. Hmm. So here also they have done the same thing. Hmm. Here basically they have done uh, like equated this P atmos. They have started from P1. Hmm. So they have started from P1 and they have worked their way up to P2. But we have done the opposite, and the opposite actually makes more sense because we already know the P atmosphere. We know P atmosphere. Our unknown is P1. So from our known quantity, we can find out P3 first. Hmm. We can find out P3, then we can find out P4, and then we can find out P1. Okay. Hmm. Yeah. So this is the last question. Hmm. So uh, do you have any doubts from today's session? So we covered first. We covered this surface tension. Hmm. How to find out surface tension from this arrangement of a film and a wire, force on a wire. So this figure explains it. So we have like two tangential surface tension forces on this wire, and that is counteracting whatever the force is there. So this force is to gamma into the length of the wire. So this we did. Then we did capillary phenomena, the capillary rise phenomena. So we solved one problem. This is the excess pressure problem, and then this is again capillary rise phenomena, like capillary dipping for mercury. The concept of this capillary rise and then we had one question where bulk modulus was asked, and then we had this hydrostatic. Hmm. So hydrostatic questions, I think you will be able to solve. Just mark the points and you can find out the pressure. Hmm. Okay. So do you have any question?
No, sir. Sir,
Okay. Yeah.
we have discussed that pressure that manometer questions. So, what if the
Mm-hmm.
manometer is in inclined position? So, in that case, we have to change the formula or like the same formula will work.
So let's say we have an incline manometer. That's so we had that pressure chamber, right? Pressure chamber problem.
Yes, sir.
So there is a like gas inside, and there is a incline manometer, for example. So something like this. That's what you are talking, right?
Yes, sir.
Okay. So let's say the liquid is here, and here the liquid is up to here. Uh, oh, since this is a pressure chamber, liquid should be actually above. Wait, let me draw it. So let's say the liquid is here. Okay. So what you have to basically do, so this is basically a continuous medium, right? This liquid is a continuous medium. Hmm. So the pressure change between these two ends is always this height gain, this height. Hmm. So no matter what is the angle of your angle of this manometer, it is always this height gain. So if this height is h, then your pressure is rho g. The pressure change is rho g. So if this is P1 here and inside it is P2, then your P2 minus P1. The higher pressure is P2. So P2 minus P1, this is equal to rho g. Now, if this h is not given, instead you are given this capital H. Let's say this length is given. Okay, and you have this theta. Then you can find this out. Hmm. So basically, what this is like a right angle triangle, and this is theta angle, and this is h, and this is small h. So your h sine theta is your small h, right?
Yes, sir.
Hmm. So always you are worried about this perpendicular height, this small h. Hmm. Okay. This is what you are asking, right? Have I cleared
Yes,
your
sir.
doubt? Yeah. Okay.
Yes, sir.
Uh, So any other question?
No, sir.
Okay. Okay. Then we will meet like in the next week session. Hmm. I'm
Thank you, sir.
closing. Yeah. Thanks.